This slide introduces constrained linear regression, specifically the cnsreg command in Stata, as a tool to bridge the gap between economic theory and empirical data. We often face a dilemma where empirical data is noisy or multicollinear, leading standard OLS estimates to violate fundamental economic laws, such as a positive relationship between price and demand, shown in the left plot. The solution is cnsreg, which allows us to impose prior theoretical knowledge onto the statistical model. As shown in the right plot, the constrained model follows a theoretical structure, a negative slope for demand, despite the data noise. Our objective is to learn how to estimate, interpret, and validate models where coefficients must satisfy specific linear equality restrictions.
Choosing the right Stata command depends on the type of restriction you want to apply. If your constraint is a linear equality, like beta 1 plus beta 2 equals 1, then cnsreg is the correct choice. However, cnsreg cannot handle linear inequalities, such as beta 1 greater than 0, or nonlinear equalities, like beta 1 divided by beta 2 equals 5. For those more complex constraints, you must use commands like nl or mxpel. The key takeaway is that cnsreg is strictly for linear equality constraints. For inequalities, you'll need alternative methods like nl with parameter transformations. This slide highlights 4 common scenarios in economics where linear constraints are essential for aligning empirical models with theoretical principles. First, for production functions like Cobb-Douglas, we apply a constant returns to scale constraint, where the coefficients for labor and capital sum to 1. This represents the idea that doubling inputs leads to a doubling of output. Second, in demand theory, price homogeneity is enforced by requiring the sum of price coefficients and the income coefficient to be 0, preventing money illusion. Third, symmetry is applied to cost functions based on Young's theorem, ensuring that cross-price effects are identical, or beta ij equals beta ji. Lastly, for time series data, seasonality smoothing constrains the sum of seasonal dummy coefficients for the 4 quarters to 0, reflecting a net zero seasonal effect over a full year. These constraints help bridge the gap between raw data and economic logic.
In this slide, we explore the fundamental trade-off between standard OLS and constrained regression. Ordinary least squares is unbiased if the model is correct, but because it ignores theoretical priors, it often suffers from higher variance, visualized here by the wider distribution curve on the left. On the other hand, the cnsreg command allows us to enforce theoretical structure, which buys us precision. This leads to lower variance and smaller standard errors, shown by the narrower, taller distribution on the right. However, this efficiency comes at a cost. If our theoretical constraint is wrong, the estimator becomes biased and inconsistent. As the summary highlights, constrained regression is a way to trade potential bias for greater statistical efficiency, a concept rooted in modern econometrics, as discussed by Bruce Hansen in his 2022 text.
The mathematical objective here is to minimize the sum of squared errors, or SSE, subject to the linear constraint R beta equals R. Stata achieves this by computing a projection matrix T and a shift vector A. This reparameterizes the model so the estimator solves for a reduced vector, beta C, using the relationship beta equals T times beta C plus A. The process involves 3 specific steps. First, transforming regressors into the reduced space. Second, running OLS on these transformed variables. And finally, projecting the results back to the original parameter space. The 3D coordinate system on the right illustrates this concept visually. You can see a cloud of data points being projected onto a 2D plane known as the constraint surface. The resulting vector, beta constraint, is the best fit estimate that satisfies the predefined theoretical rules. Think of it as squashing a 3D cloud of data onto a 2D plane that represents our economic theory. This geometric projection ensures our empirical results remain consistent with our prior theoretical restrictions. Before we move into execution, we must ensure certain assumptions and identification rules are met.
This slide outlines the fundamental assumptions and identification rules necessary for using the constrained regression command in Stata. Starting with the core assumptions, we have three main pillars. First is linearity, which means every constraint must be a linear combination of parameters. For example, 2x plus 3y equals 1 is valid, while x multiplied by y equals 1 is not. The second pillar is consistency. Constraints cannot be contradictory, such as demanding x equals 1 and x equals 2 at the same time. The third pillar is strict exogeneity, which assumes the error term is uncorrelated with the regressors in the underlying model. Moving to the identification update in Stata 15, there has been a significant change from the old rule where the number of constraints, c, had to be strictly less than the number of parameters, p. Stata now supports cases where c is greater than or equal to p. If c equals p, the cnsreg command functions as a solver for a system of simultaneous equations. If c is greater than p, it acts as an algebraic checker to ensure all parameters are consistent with the set of constraints. This allows cnsreg to be used not just for estimation, but also for the algebraic verification of parameters.
This slide explains how constraints impact the degrees of freedom and statistical significance of a model. The formula for residual degrees of freedom is df residual equals n minus p plus c, where n is the number of observations, p is the number of estimated parameters, and c represents the number of constraints. From an economic perspective, every constraint acts like a bonus observation. By reducing the number of free parameters, we increase the degrees of freedom available for the error term. Consequently, t-statistics often increase and p-values decrease because the standard errors are computed over a larger denominator, leading to more efficient estimates. Now let's dive into the first step of the process, defining constraints. In Stata, constraints are managed independently from the actual regression command. They are stored in memory slots numbered from 1 to 1999. The general syntax is straightforward. You use constraint define, followed by a number for the slot, and then the equation or expression you want to enforce. Let's look at three common examples. First, equality to a constant. Here, we define constraint 1 so that the price coefficient is exactly 0. Second, equality between variables. In constraint 2, we are stating that the coefficient for weight must equal the coefficient for length. Third, a linear combination, which is often used for testing homogeneity. In this case, constraint 3 defines that 2 times the weight coefficient plus 3 times the length coefficient must equal 1. A quick pro tip here. Always run the constraint list command to verify what you've stored in those memory slots. Also, be aware that Stata won't actually check if your variable names are correct until you run the regression, so double-check your spelling beforehand.
Moving to step 2, let's look at the actual syntax for the cnsreg command. It follows the familiar Stata regression format. You start with the command name, followed by your dependent variable y, and then your list of independent variables. Optional qualifiers like if and in can be added to filter your dataset. The most critical part, highlighted in the orange box, is the constraints option. This is a required field where you list the numeric IDs of the constraints you defined in the previous step, such as constraints 1 or a range like 1 through 3. Finally, you can include other standard regression options. If you prefer using menus, the path is statistics, then linear models, and finally constrained linear regression.
When configuring the cnsreg command, several options are vital for robust analysis. First, the VCE/robust option is essential. Real-world economic data rarely maintains constant variance, and this ensures your standard errors are heteroscedasticity robust. Second, the collinear option is necessary when your theoretical constraints resolve identification issues that would otherwise cause Stata to drop variables. Third, to maintain clean and readable log files, no CNS report suppresses the technical algebraic block in the output. Finally, you can use the level option to modify the confidence interval from its default 95% value. These tools give you fine-grained control over your constrained model's estimation and reporting. In this practice case, we're modeling car mileage, or MPG,
based on two inputs, weight and length, using the classic auto dataset. The model is specified in logarithmic form, so the coefficients beta 1 and beta 2 represent elasticities. Our hypothesis is constant returns to scale. However, unlike a standard production function where we expect a sum of positive 1, here we constrain the sum to negative 1. This is because in this engineering context, weight and length are inversely related to mileage. As the car gets larger and heavier, fuel efficiency decreases. By imposing this theoretical constraint, we ensure our statistical model aligns with known physical principles of automotive engineering. Let's look at how we prepare these variables and define this specific constraint in Stata. In this first practical step, we prepare our dataset for constrained regression. Our goal is to estimate elasticities, which requires a log-log model specification. We start by loading Stata's built-in auto dataset using the sysuseauto clear command. Next, we generate log-transformed versions of our variables, ln_mog, ln_weight, and ln_length. By using the natural logarithm function ln, any coefficients estimated using these variables will represent the percentage change in the dependent variable for a 1% change in the independent variable. Finally, we verify the creation of these variables using the describe command with a wildcard. The output table shown at the bottom confirms that we now have 3 new float-type variables, each with descriptive labels indicating they are the log of, mileage, weight, and length. This data preparation is essential because it transforms our physical measurements into a scale suitable for elasticity interpretation, which is a common requirement in economic modeling. Now, let's move into the practical application within Stata. In this second step, we are defining the specific constraint we've derived from our theory. We use the constraint defined command, assigning it an identifier, in this case, number 1. We then explicitly state the linear equality. The sum of the log weight and log length coefficients must equal -1. It's always a good practice to verify your work. By running the constraint list command, we can see that Stata has stored the restriction exactly as intended, as shown in the output box at the bottom. This constraint is now ready to be applied in our constrained linear regression. Now we move to practical step 3, estimation and output. Here we run the cnsreg command, including our dependent variable, independent variables, and the specific constraint defined earlier. Notice the VCE robust option used for robust standard errors. In the output, Stata explicitly lists the applied constraint. The sum of ln weight and ln length equals -1. Looking at the results, we have coefficients of -0.65 and -0.35. As shown by the sum check, these add up perfectly to -1.0, confirming the constraint is correctly applied. We also observe that with 74 observations and a root MSE of 0.1234, both coefficients are statistically significant. Once we have estimated our constrained model, the final step is verification and diagnostics to ensure our theoretical assumptions align with the reality of the data. First, we perform a visual check. By predicting the residuals and plotting them against one of our independent variables, like ln weight, we look for any discernible patterns. Ideally, the points should be randomly scattered around the zero line, suggesting that the model has captured the main structure of the data. Next, we conduct a formal statistical test. The question here is, does the data actually agree with our theoretical constraint? To find out, we run a standard unconstrained OLS regression and then use the test command to evaluate the restriction that the sum of the coefficients equals -1. Looking at the output, we see an f-test with a p-value of 0.5042. Since this p-value is significantly higher than the 0.05 threshold, we fail to reject the null hypothesis. This means that our statistical evidence strongly supports the constraint we imposed based on theory. This step completes the rigorous workflow of constrained regression estimation. To wrap up, let's review the step-by-step workflow for implementing constrained regression. It begins with theory, where you formulate your hypothesis, like constant returns to scale or symmetry, based on economic principles. Next is the define phase, where you use the constrained define command in Stata to store your theoretical rule. Third is the estimate phase, where you run the cnsreg command while specifying your constraints. Finally, you must verify the model by checking residuals and conducting post-estimation tests to ensure the data actually supports your theoretical assumptions. In short, cnsreg is a powerful tool for aligning models with theory, resulting in greater statistical efficiency when the theory is valid.